This video reviews pages 29 to 31 in your lecture tutorial book. It's a section called Melting Rocks and Plate Tectonics. I've divided the 3 pages into 5 sections here just for the convenience of showing it to you in this presentation. I'd like you to pause the video if you haven't tried these pages yet and see how well you do after you've answered them by checking with my answers. The objectives here are to identify the locations that magma forms based on plate tectonic boundaries or surface features, and to determine where melting occurs and why for various plate tectonic scenarios. The diagram below is showing a cross-section of a subduction zone. It's an ocean plate going below a continental plate, and the ocean surface is shown here in a dashed line. Rocks can melt when the temperature increases, the pressure decreases, or water is added, sometimes called volatiles. Deeper you go below the earth, the hotter it gets. And also the pressure gets greater as you go deeper. So if rocks rise to the surface, the pressure decreases. So on the left, I have the questions that are related to the diagram. I've put the diagram on the right so we can look at them at the same time. This page reminds you that at convergent plate boundaries, rock melts in locations where there are the following conditions. First of all, the temperature has to be high enough for the rock to melt. And secondly, water is typically added to the mantle by the subducting plate, and that water lowers the melting temperature of the asthenosphere. So, based on these requirements, in which location does rock melt at a convergent plate boundary with subduction? So you look over here on the right at the diagram, and the answer is C. Draw an arrow on the diagram to show how the less dense magma rises up and erupts to become a volcano. Now let's look at these 4 students discussing where the rock melts in this diagram. The first student picked A because they think that there's enough friction to melt rocks at the trench. It's certainly true that there's high pressure there, but remember, high pressure actually inhibits melting. So the temperature is too low here for melting, and the pressure is not low enough either. Student 2 picked B because that student says, well, I think the magma forms where it erupts from the volcano. And that's certainly a logical thought. However, it's also too cool there for the rocks around there to melt. Otherwise, everything would be melting at very shallow levels in the crust. And we know that the crust is solid. Student 3 picked C, which we've already said is the correct answer, because it's hot, it's deep, and it has water added. The volcano is also right above position C, which tells us that the magma is coming from C. The student that picked D said the subducting plate is deep, and that's where things might melt. And D could certainly be an answer if there was a volcano above it, but there's not. So we're going to go with C as the region that's melting. Part 2 looks at divergent plate boundaries, and I have put some green arrows here to remind you the way the plates are moving. The first question asks, why do rocks melt at E but not F? And the reason is that there's lower pressure at E than F. And remember, lower pressure, that changes the melting temperature, and rocks melt. The next question asks about E and G, and notice these are at the same depth. Why do rocks melt at E but not G? And that's because it's hotter directly under the mid-ocean ridge, because that's where new material is welling up from the asthenosphere. At position G, things are cooling down as they move off the central magma source. Part 3 asks about hotspots, and I drew a little cartoon here reminding you that there's a mantle plume feeding this area. So why do rocks melt at K but not J? Well, the temperature is hotter. This mantle plume is coming up and it's very hot. What about rocks at K but not L? Again, these are at the same depth. And again, it's the temperature. K is very hot because the mantle plume is feeding it. Finally, part 4 puts all of these things together. I've drawn some green arrows here to show where the subduction zone is, the divergent zone is, and the mantle plume is rising. Question 8 says, on the cross-section, put an X on the 3 locations where rocks melt to form magma that will eventually move and erupt at the surface. So in the subduction zone, we have magma melting right down here. The hot spot, we have melting at the top of the plume. And at the divergent plate boundary, we have melting where the 2 plates are moving apart. Explain why the rocks melt at each of these locations. So I've labeled them location 1, 2, and 3. So melting at location 1 is what we call flux melting. It's because volatiles or water are added to the asthenosphere and they lower the melting temperature. At location 2, it's because we have heat being added from below. The mantle plume is very hot. Location 3 is decompression melting, where material rises to lower pressures and thus starts to melt. On the cross-section above, draw a star at each of the 3 places on the surface. So hopefully this is pretty straightforward. At location 1, we even have a little volcano. Location 2, we have an island forming. And location 3 would be at the center of the divergent plate boundary. Next, draw an arrow from each melting location to the surface where the lava erupts. And I'm going to blow up that picture up top so you can see this better. Same picture as before. And in every case, we're basically going to connect the X to the star, indicating that magma rises straight up. The last question says to compare your answers to questions 8 through 11 with the work you did earlier. And since I gave you the answers, these are all correct. And that's melting related to plate tectonics.